Now I am going to discuss about linear algebra. In that linear algebra, I am going to discuss about basis and dimension. Okay, the definition of basis is let S be a basis of a subset of a vector space V. Then basis should satisfy the two conditions, that is S should be a linear independent and S should span V. So these are the two conditions to be satisfied for the basis, and basis can be written as the by using the notation beta 1 and beta 2. So basis should be in the ordered set of a linear independent vectors which spans V. Okay, the next theorem is about let S spans V, that every vector V can be written as a linear combination of a vector in S. Let S being the basis of which it should satisfy the condition that let S is equal to V1 to Vk be a basis for V, and this V can be uniquely represented as a linear combinations of a vector in S, and this is called a span of V. And how to write the span of V is it can be written as a linear combinations of a vector in V. So this is about proof. Proof is let V is equal to, these are the linear combination, that is A1 V1 plus etc. An Vn, which is equal to B1 V1 plus Bn Vn. Then this A1, that is we have to take the coefficients for each vectors, that is A1 minus B1 into V1 plus etc. An minus Bn into Vn, which is equal to 0. So S is a basis for V, then linear V is called, it is a linear independent, and the above implication shows that A1 minus B1 which is equal to etc. An minus Bn equal to 0, and we conclude that A1 equal to B1 and etc. An equal to Bn, and this is the span for V. The next theorem is about let see S is a span of a vector space V, then there is a subset S which is a basis for V, and it can be written as Vk is equal to A1 V1 plus etc. Ak minus 1 Vk minus 1. So linear independence means which has no redundant vectors. If it is a linear independent, for a vector we have to find the linear independent means there should be no redundant vectors, and this is a proof for that theorem. Next is dimension. Dimension means the size of the vector, that there should be at least two vectors in a vector space. So here dimension means there are way to measure the dimensions of a vector space. So one of the way is represented in the theorem, that is let S is equal to V1 to Vn is a basis of a vector space, and T is equal to W1 etc. Wk, which is a linear independent set of vectors in V, then k less than or equal to n, and this is the one method to find the dimension of a vector. Okay, the next is a theorem, let S is equal to V1 to Vn be a linear independent set of vectors in a vector space V, then there is a vector Vk plus 1 etc. to Vn. So such that V1 to Vk plus n etc. to Vn is a basis for V. Let V be an n dimensional vector space and S be the set of with n vectors, then this should follow the three condition, that this should be follows an equivalent condition, that is S is a basis for V and S is a linear independent and S spans V. Next is an example. Here the example is for to find the basis, that is let V equal to P3 which means a polynomial, and S is equal to 1 t square t cube, then we have to show that S is a basis for V. So we must show both linear independence and span. So to find the basis we have to find the linear independent and span of a vector. So first linear independence means we have to take it as let C1 of that S vectors, that is C1 of 1 plus C2 of t plus C3 of t square plus C4 of t cube, which should be equal to 0. Now taking the coefficients, so we know that the polynomial 0 means if and only if the coefficients are all 0. So which means here C1 equal to 0, C2 equal to 0, C3 is equal to 0, C4 equal to 0. S is a linear independent of a set of vectors in V. Next we have to find the span. So span means it can be represented as a linear combinations of vectors. So in general P3 is given by A plus BT plus CT square plus DT cube. Coefficient of B and CD which is comes under this S. Okay, so this can be written as A plus BT plus CT square plus DT cube. Now we should find the constant, that is C1, C2, C3 and C4, such that both should be equated, that is C1 of 1 plus C2 of t plus C3 of t square plus C4 of t cube equal to A plus BT plus CT square plus DT cube. So we just let how to find this means taking the coefficients, that is C1 equal to A and C2 equal to, taking the coefficient of t, that is C2 equal to B and C3 is equal to C and C4 equal to D. So this spans V. So from this we can find the span of a vector. So from this we can conclude that this vector is both linear independent and also spans. So S is called the basis for V, and in general the basis 1, t square etc. t power n is called a standard basis Pn. So next example is about, show that S is equal to V1, V2, V3 and V4, where V1 is a matrix. So in matrix form also we can find the basis. So basis for V equal to M 2 cross 2 matrix, this is. So here now we should find this matrix is linear independent as well as it should be a span of V. And the question they have given us, V1 is equal to 1 2 0 0 and V2 is 1 0 2 0 and V3 is 1 0 0 2 and V4 is 2 1 0 0. So now we need to show that V is a linear independent. So linear independent means C1 of 1 2 0 0 plus C2 of 1 0 2 0 plus C3 of 1 0 0 2 and C4 of 2 1 0 0, which should be equal to 0. So now the C1 should be multiplied to each matrix, that is C1 into 1 is C1 and C1 into 2 is 2C1, next is 0 0 plus C2 0 and 2C2 0 plus C3 0 and 0 2C3 plus 2C4 comma C4 and 0 0, which is equal to 0. Now we shall write this as in equation, that is taking the first row, that is C1 plus C2 and C3 plus and 2C4. Next one is, see the second line, that is 2C1 plus 2C4, 2C1 and 0C2 and 0C plus 0C3, next one is 1C4. So which means for the second equation 2C1 plus C4 equal to 0. Similarly for third equation is 2C2, that is 0C1 plus 0C2, 2C2 plus 0C3 and 0C4. So which means 2C2 is equal to x3 and 2C4 is equal to x4. That is 2C2 is equal to 0 and 2C3 is equal to 0. So now the corresponding homogeneous equation is what? Ax is equal to 0. Instead of x we shall keep here as C, that is AC is equal to 0. So with this we have to write it in the determinant form, that is taking the coefficient of C1, C2, C3 and C4 in the first equation, that is 1 2 1 1 1 2, next one is, first one is 2, next one is 0 and 0, next is 1 and third one is 0 C1 and 2 C2, 0 C3 and 0 C4. Next one is 0 C1, 0 C2, 2 C3 plus 0, 0 C4. So here the determinant value exists, that is determinant is equal to minus 12. So if the determinant is 0, non-zero means it is clearly known that it is a linear independent, that is it will exist, there is only a trivial solution exists. So therefore C1 equal to C2 equal to C3 is equal to C4 equal to 0. Next one we have to find the span. We have seen linear independence, next we have to find the span of a vector. So span of a vector is what? We have to take the, write it in the form of linear combinations. Okay, C1 of 1 2 0 0 plus C2 of 1 0 2 0 plus C3 of 1 0 0 2 plus C4 of 2 1 0 0, which is equal to that A11, A12, A21 and A22. So this is, again we have to multiply each C1 in the first matrix and C2 in the second matrix and C3 in the second matrix, third matrix and C4 in the fourth matrix. So which is equal to A11, A12, A21, A22. So now we have to take the coefficients, that is C1 plus C2, for taking the first element in the first row, that is C1 plus C2 plus C3 plus 2C4 equal to X1. So, next one is 2C1 plus etc. C4 equal to X2 and 2C2 equal to X3. Next one is 2C3 is equal to X4. So, from this it is clear that since it is A is a non-singular matrix, it has a unique solution, namely this can be written as C is equal to A inverse of X. From this it is clear that S spans V. So, from this we conclude that this matrix forms a basis in the vector space V. From this I have complete the basis and definition, introduction, and also I have given the problems for this basis and dimensions. Okay. So, from this we conclude this unit. Thank you.